seems to be working. Oh. Hi, everyone. I'm going to make a start. This workshop is going to be about how we can use zero-knowledge proofs within Ethereum. So I'm going to sort of follow this rough overview. First, I'm going to just set the scene. Then I'm going to look into a case study. I'm going to talk about polynomial commitments a bit, more case studies, and then talk more specifically about zero-knowledge specification. I will ask questions as we go. And also, if any of you have questions, then please ask questions as we go. I'm hoping to make it feel more like a workshop and less like a presentation, so hopefully that will help with that. So first questions, which I'm going to want you to answer via a show of hands. Question 1, do you roughly know what a zero-knowledge proof is? Okay, so some of you do, some of you don't. How many researchers and engineers do we have who are actively working on zero-knowledge in the room? A couple. And how many of you have strong opinions about whether we should use zero-knowledge proofs in the consensus layer of Ethereum? 1. Okay. So to start off with, what are zero-knowledge proofs? I'm going to own to something I actually hate telling people what zero-knowledge proofs are. But so many of you do already know what zero-knowledge proofs are. So can I quickly ask you to turn to the person next to them and give a quick explanation where you can use the Where's Waldo example if you like. Go on.
Chaque participant explique à son voisin qu'est-ce que zero knowledge proof.
10-second warning.
Non, c'est bon en fait.
Okay, I'm going to assume that that was the best explanation that's ever been given. In terms of where zero-knowledge proofs are currently being used in Ethereum, I would say that on the application layer, they are being used almost everywhere you look. And I gave a number of examples on the slides. We've got the decentralized identity, private token transfer, reducing bribery, on-chain game engines, zero-knowledge bridges, private DeFi, scalability solution. When it comes to the core layer, however, I would say that right now, maybe arguably, ECDSA signatures are like a type of zero-knowledge proof. That's about it. And I would say that there are some fairly good reasons for this. By the core layer, by the way, I mean the layer which is deciding which transactions do and do not get included on the Ethereum blockchain, as opposed to what's going on inside a smart contract. The core layer, because this is sort of our key thing which is defining whether we're live, whether the system is working at all, people are relatively conservative. There's some reasons for this. Probably the biggest one is that we can't really depreciate old code. Once you have code, it has to be maintained forever. Particularly with zero knowledge, we've got a bit of a problem that bugs might require expert knowledge to fix. So we can't just go up to some random developer and be there like, we have a problem, please fix. Like, we would need a specialist on that case very, very quickly. And a third reason is that there is a strong preference for simplicity at the core layer. And for all of the really good things you can say about zero-knowledge proofs, they're not very simple. However, they're also really, really useful. And there are a number of situations where we are considering using zero-knowledge proofs at the core layer, absolutely including roll-ups, private lead elections, proof of validator, inside the randomness beacon. There's There's a bunch of different places. One of these reasons is sort of I'm on the cryptography research team, and when they come up to me and they're like, do you have a solution? I only have one solution. It's use zero knowledge, and if that doesn't work, then I'm kind of out of ideas. So when they come back to me and they say, but this is really complicated, I've got a real problem. So really the core question of this workshop is going to be, what can we do to mitigate the risks of implementing zero-knowledge proofs and cryptography generally? As a cryptographer, I have some philosophy about this, which is sort of rooted from, well, academia. And some of this philosophy is going to be good philosophy, which is really going to help with making sure that we get things right. And some of it is maybe going to be less practical philosophy, where inputs from developers and from people from other spaces might be very helpful. But one thing which I'd say that cryptographers are very good at is answering the question, what is my scheme even trying to do? It sounds like a simple question, but actually this is something where you have to be very careful about the details, because if you're even just slightly off, it can affect things in ways that you wouldn't expect. Kind of related to this is, what security properties do I want to achieve? Do I want it to be like private? Do I care about liveness? Do I care about authenticity? Do I want it to be composable? So that would mean that I can use it as like a plug and play thing in other protocols. Do I care about adaptive security, concurrent security? Lots of different questions along these lines. And I'd say this is something where developers sometimes have a slightly better insight as to which properties are genuinely important in their scheme. This is for good reason, right? They're very familiar with their scheme. They know what they need. They know what they want. Whereas if you're just sort of coming from a different background, being there like, I think you want this, sometimes you'll get it wrong. The other question that they tend to ask is, what is my theoretical model of computation? And this is saying that if I'm going to abstract things away and sort of say, here's how I'm going to analyze whether I think it's secure or not, what do I consider to be a valid model of computation? I'm not going to spend too much time on that. The next step in the process is to specify the scheme. And this is an area where I would say cryptographers are, in general, a bit less precise than the general technical population. Don't get me wrong, some specifications are better than others. There are some very good quality ones out there. But there are also less good quality ones out there. Typos are not that uncommon. Sometimes there's an implementation, but it will typically be a proof of concept implementation done purely to give an idea of speed. Also, sometimes they will use black box subprotocols that are not fully specified. This, again, is for quite good reason, because it gives a developer some freedom in how they want to choose to instantiate it, and it just sort of modularizes out some of the complexity when you're trying to analyze security. Probably the biggest thing that most cryptographers would agree with is that security reductions are really important. So the idea here is that you want to demonstrate that if my scheme doesn't satisfy my security requirements, whatever those happen to be, then I can break some hardness assumption. I personally think of these as very high-quality unit tests. Not to say that they're going to like catch all the problems, or that if you have a security reduction, everything is fine, but more to say that if you don't have it, then you probably haven't done your due diligence. Some security reductions are better than others, and one thing that I would note is that peer review is not the same as a thoroughly audited security reduction. There are many, many layers between here's my research paper and what I would consider to be something ready for implementation. So now a couple of questions to you. Can you think of any examples where there are one or more Ethereum developers that have set out their design goals really, really clearly, and can we learn from them? Or alternatively, is there a scheme specification written by a cryptographer that you wish other cryptographers would learn from, and why? Feel free to answer either question. Can I have hands for anyone that wants to answer? Okay. Are the questions too hard or too easy?
We don't know, so smart.
Ah, okay. So I'm sort of saying, do you know any of examples where people have done them well? And the answer is no. Okay, I'll take from that. I'll take from that. let me move on to a case study, which is a case study that I have sort of personally been working on a bit, which is a case of shuffle arguments specifically for leader elections. So this is, in my mind, quite a fun application, which is related to the core consensus layer of Ethereum. The aim here is to choose a validator to update a future block. The current way that we're doing this is that RANDAO is going to output some randomness, which is just going to randomly determine the validator to run that update. The problem with this approach is that the winning validator is like public, everybody knows who they are, and this makes them very susceptible both to bribery attacks and to DDoS attacks. I've heard people argue that the bribery attacks are maybe more of a concern than the DDoS for reasons to do with people being able to keep their address private if they want to. But either way, this is something where we kind of know how to solve it. And the way that we can solve it is we can run what's called a single secret leader election. Here, every validator has a tracker that they alone can identify. And the trackers, which are kind of encrypted in a way, are progressively shuffled by different parties. At the end of the shuffling process, it will be secure, as in like the winner of this shuffle is going to be unknown, provided a fraction of the parties don't collude. Where that fraction is something that is determined by the system. The current proposal for doing this is called the Whisk proposal. And I would say that there are 3 layers to this proposal. We have the consensus and permutation logic. We have a random beacon, and we have a zero-knowledge proof. When it comes to the permutation logic, there is a very nice paper by my colleague Mark Simkin and his co-authors, which is giving a formal argument as to why we would expect it to be the case that if enough people have shuffled, nobody's going to know who the winning validator is. Possibly the thing that's more relevant to this talk, though, is the zero-knowledge proof. And there exists a special purpose zero-knowledge argument for shuffle arguments, which has some very nice properties. Probably the biggest one is it's quite a lot simpler. And in particular, you don't have to write out the constraints of what you're trying to prove, because it's special purpose. It's only proving this one thing. So if any of you have ever sort of worked in SIRCOM or any things like that in order to say, this is what I'm trying to do. With this particular scheme, you don't have to do that. The protocol which we're suggesting to use is a slight adaptation of a popular protocol by Bayer and Grott, and it only uses group operations and hashes. However, even with this much simpler scheme, I'm going to say that there was still a lot of concern about the complexity being suggested. I personally tried to tackle some of these concerns about the complexity, and really with the only trick that I knew how, which is just more documentation, and I had some specific documentation goals. Probably the biggest one is as much modularity as possible. I wanted it to not only be the case that you can just plug in this zero-knowledge proof and it doesn't affect the other parts of the system, but I also wanted that the algorithms used within the zero-knowledge proof itself were very much sort of plug and play. And I don't mean UC by this, which cryptographers would mean something specific by. I literally just mean that the inputs and the outputs are very clearly defined, and if it's calling a sub-protocol, it's clear how it interacts with that sub-protocol. Cryptography reductions are auditable. I won't go as far as pretty, but they could at least be audited by somebody who knows what they're doing. And possibly one of the biggest ones, optimizations are kept very, very simple and are explained. So in particular, if there was an optimization which made things just a little bit better, but came at the cost of making the protocol more complex, then we didn't include it. Okay, so some more questions. These didn't go that well last time, but hopefully these should be a bit easier. I'm going to actually start with question 2. Security reductions. So you see my picture there. It's not very pretty. I would say that they're never pretty or easy to understand. Like if you have some documentation and you're there saying, here's my security proof, most people who are reading the documentation are going to look at that and go, I don't want to read that. But at the same time, I do think they're very important to include for reasons of, making sure that you've done your tests correctly. So would you personally prefer that they appear with the protocol or in separate documentation?
I would say in the annex of the paper, the part you don't read usually.
In the appendix, okay. Yeah, I think there's some good reasons for including it in an appendix. There are some downsides, being that when it's in an appendix, people can sort of, assume that it's not going to be read, and then things get even worse. But there are the upsides that developers then don't have to read that part. Question 1, I think I'm going to do by show of hands. Does anyone think that it's possible to overdo modularity? Anyone willing to say why?
Yeah, sometimes at each interface of modules, you might be sort of compromising or making some, like compromises, or there's some extra conversions to meet an interface. So the more modular it is, there's perhaps more interfaces, so there's perhaps just more of that conversion rather than the core of what you're trying to do.
So like you'll be trying to introduce modularity, and in doing so you'll make the scheme worse. Is that what you're saying in some places?
Yeah, potentially like those, so the interface points between modules might add complexity.
It also makes it very hard to audit because there's so many modules and you have to like bounce back and forth. So yeah.
So is that a sort of concern about it's harder to get a high-level view of what's going on? That makes sense. And the third question, again, I'm going to start with just a show of hands. Has anyone sort of come across a situation where security flaws have been introduced due to bad optimizations? How many of you are auditors by chance? Again, if you want to give some examples of that, keep your hand up. Otherwise, I'll move on. Yeah?
Easy classic one, having a RSA modulus being picked by multiplying common prime, just computing a GCD. You can break the factorization, for instance. There are so many of them.
Go on, behind you as well.
Well, there's a classical one for the optimizer for Solidity. They cached the check hash if you were using inline assembly, and it was an optimization, but they did up breaking up. Like, it was a pretty obscure edge case, but you could be bricked by having a cached hash there. So it's one of the examples.
Okay, so don't cache your hashes. Thank you. So after the step of writing down sort of the what am I even trying to do, what's the high-level look of my protocol, what's going on, I would then say the next step into getting stuff productionizable is to have more practical specifications. And proof-of-concept client implementations are sort of a big next step. These are typically written by developers. In the particular case of the single secret leader election with Whisk, we have 3 implementations at the moment, one in Rust, one in Python, and one in Go. I've got the links in the QRs codes to those there, and some very good work went into all 3 of these. I don't know if anyone responsible for writing these is in the room. If so, maybe make yourself known to me. So when it came to these specifications being written, I would say that there were things that I was able to help with in a sort of interactive back and forth process, and things that maybe I wasn't the correct person to help with, and maybe there would be other people within the design space who would be better people to ask. Questions that I could help with absolutely includes, is this a typo? To which the answer is always yes. If you've gone to enough effort to read the documentation to get to the point where they're like, this doesn't look right, is it a typo? It probably is. If I optimize this part, is it still secure? Usually it's not. Usually there's a reason that optimization isn't included, but not always. Can we not have the tracker? This is like something that's quite specific to the Ethereum consensus protocol. I'm going to try and explain it from high level. I apologize if it's not that simple to understand. But basically this thing that you're tracking which says, have I won the election or not? That is the one thing which is really interacting with the other consensus parts of the algorithm. Like that's the only thing where they're like, you have to change the base consensus specs to allow for this like long-term tracker. So people didn't really want that. They would prefer to have it so that you can just use your BLS public key and use that as your tracker. I kind of don't like this approach. There's a couple of reasons, but probably the biggest one is your BLS public key is like your validator key. So this is a thing which all of your validator funds are tied to. And I kind of don't like the idea of that particular very high value public key being used here, there, and everywhere, rather than just being tied to this one thing that it's trying to keep secure. In terms of questions I was less able to help with, but there were other very intelligent people that could help. How should we implement feature so hash functions? This is a very big question. And which PRNG should I run? So this is, again, very much sort of saying, there's all these different PRNGs out there. Which one is good for this use case? Again, this is getting to the level where I might not be the right person to ask. Okay, so some more questions. The first question is a bit vague. What do you believe is the ideal process to translate a theoretical specification into a practical specification? Because this is a bit open-ended and vague, I'm going to give people a brief second to sort of put their hand up if they want to answer, but I won't linger on that one. Cool. Oh, yeah, go on.
You could write very extensive tests first, so that any practical implementation could be tested against the theoretical specification.
That's quite a good idea. I don't think that's currently done a lot. Practical specifications usually have tests, but theoretical ones are usually quite short of them. Go on. Sorry, over there.
Yes, so what about formal specifications that you can reason about?
Yes, they're great. Hard to do, take a lot of investment.
Well,
but
when you talk about practical specification, if it's in Python or Rust or whatever, it's an implementation rather than a specification.
I would say it's more than that. Like, there will be an implementation part, but you would also have supporting documentation, which would say all of the APIs, for example. It would say the expected inputs and the expected outputs. It would say what the scheme's trying to do, this sort of thing. You wouldn't just have the code, ideally. Okay, next question. How can we educate the Ethereum community about which projects have very high quality documentation and are ready to use, and which don't?
Why? What are you trying to achieve?
So we would be trying to say, if you want to use this protocol, then we have some faith that there has been a level of due diligence with the documentation, or maybe we don't and it's just a research paper or something that's hot off the press. I would say, like, getting an insight as to which projects are in which status is something which is quite hard. So is there anything we can do to sort of help people identify? Oh, go on.
Yeah, just sort of following on from the why, I guess it's, yeah, who's coming to it and where. So if it is on, say, ethereum.org website somewhere, perhaps just an ordering or a simple like traffic light system to say it's like a band of quality in a sense, like just make some projections for the user just to simplify it for them to say, under the hood, these things are well documented and others are not, and just have it in that order. So if someone's coming to use it, they can very intuitively see where things are.
Would you sort of be open to extending that to just labels where you can sort of say, this is where the documentation is currently at, and then it gets upgraded over time? Because I think that might be, if nothing else, less insulting.
Yeah, just something like that, just to see where it is. Yeah.
Yep, sounds good. And the last question, how do we incentivize the production of high-quality documentation? Because this takes time and effort and is often not that rewarding. So is there something we can do in order to sort of give people, if nothing else, some sense of status for having gone through this process?
Quickly add, yeah, maybe in that place where people come to see that, they might just put like a like or a thumbs up and say, hey, I'm interested in this one. And if it's lower in the list in terms of degree of documentation or quality of documentation, then that might be an incentive as well, or even bounties if you want to go further.
Yeah. Okay, I'm going to move on. Polynomial commitment schemes. I'm going to guess that not everyone is going to know what a polynomial commitment scheme is, but again, show of hands, who does? Okay, a good number, about half, I'd say. I would say, as a general rule of thumb as to like how it's used, why it's used, it's kind of a data compression technique. So it's typically used when we want to avoid sending very large amounts of data, and we just want to sort of send a small token which says, the data exists, I promise. From a technical standpoint, there are kind of like two phases. There's a commit phase where you basically generate that sort of small token that says the data exists. And there's also an evaluation phase, which sort of says, this function outputs this value, which can be computed by the person who knows the data, knows the function. And a decider is just going to take that and say, do I believe you or do I not? So that would be the evaluation phase. There are lots of different polynomial commitment schemes that we are aware of, and all of them have very different trade-offs. So fries, which are the ones that are used, for example, in Starks, are typically a bit bigger, but they are based on error-correcting codes, which have this very nice property for long-term security, being that the only thing that you really are depending on is hash functions. And if your hash function breaks, you can always just replace it with a better hash function. Another big and popular one is KZG. These rely on pairings. They are the smallest polynomial commitment scheme that we're aware of. We can't make it get smaller than that. You can't really get a faster verifier than that either. But they do come with the downside that you have to go through a trusted setup process, which is like an initial multi-party computation, which can be a bit of work. Bulletproofs is another big one. These again have quite small commitments, but the verifier is quite slow, as in the decider, which can be an issue in some places. Two other ones, which I'm going to briefly mention, are lattices and darks. The reason I'm only briefly mentioning these is because they're possibly a bit less explored and a bit less ready for implementation than the other three at this current moment in time. This could change. In terms of where we're thinking of using polynomial commitment schemes in Ethereum, zero-knowledge proofs are something which sort of we're both hoping for at the core layer and the application layer, and are a sort of big use case of them. But there are actually quite a lot of other use cases. Certainly at the application layer, we've got lots of things to do with secret sharing, consensus algorithms, distributed key generations. At the core layer, though, we have three situations where I know they're being suggested. ZKRollups, that's related to zero-knowledge proofs, so I'm not going to go into that one. We also have Verkle trees and data availability. So vertical trees are a suggested upgrade, which are really being suggested as a scalability solution. So currently we're using fan-in to Merkle trees. The idea here is that you want to replace them with fan-in n vectors. If you were to just do this replacement outright, it would make the amount of data you're saying in order to say, look, this transaction exists on the blockchain, therefore I can do this. It would make it quite a lot slower because at each layer you'd be sending more data. But if instead you have those vectors being committed to via a vector commitment, which is kind of a special case of polynomial commitments, then you end up with the amount of data that you're sending actually being very, very small. This is something which we do know how to do over the BLS curve, which is quite important because BLS curve is already being implemented at the core layer, so we wouldn't sort of require additional curves and additional pairings. One of the reasons we can do this is that there are inner curves, so inside curves, where we can do the vector commitments. And in particular, there's a curve called Bandersnatch, which is very, very efficient for this sort of thing. There are, again, good quality implementations of Bandersnatch, and there has been lots of work to sort of guarantee its security. For the application of zero-knowledge proofs, I will say more on this later, because right now we're talking more about where else polynomial commitment schemes are being seen on Ethereum. The big one I want to talk about is data availability. And the reason I want to talk about this one is because polynomial commitment schemes, which are a core building block for zero-knowledge proofs, are going to be used on Ethereum after the Denkan upgrade, probably. So this moves me on to my second case study. So data availability, definitions, and design. The basic idea of data availability is we want to shard everything to make transactions very cheap. The current state of this is the EIP 4844 proto-dank sharding proposal, but currently before the upgrade goes in, things are unsharded and one block is seen by everyone. Can I just quickly, before I delve deep into this section, give a couple of disclaimers. The first being that this is not my own work, so please forgive me if anything is inaccurate. And the second is that 4844 is not yet a full DAS solution. So we have, so some of the stuff is like what we're aiming towards rather than what will be included in 4844. Okay, so rather than having one block, which everyone verifies, instead we can shard everything in order to try and make, in order so that only subcommittees see each shard. We're still going to have it such that there is some consistency checks, and the way that this is going to be done is that everybody is going to see small commitments to each of the shards, but they won't see the full data itself. And the hope is that if there is some data on, for example, shard 2, and C3, that is a typo, C2 is inconsistent, then observers would be in a position to submit fraud proofs and say there's a problem here. The trouble is the observers can only sort of say that there's a problem if they actually have access to the data. And proving that you don't know something is not just practically, but also theoretically impossible. You cannot prove a lack of knowledge because you don't know what you're not proving. But you can prove that you do know stuff. And this, it turns out, is sufficient for us to say, look, we're going to prove that people do have the data available in order to do the checks that they need to do. And the way this is done is actually kind of similar to lots of other cryptographic consensus and consensus concepts. It's very related to verifiable secret sharing. It's very relatable to broadcast. It's very relatable to the Frye polynomial commitment scheme. There's just a few tricks that are used everywhere, I guess. I would say there's like 4 steps. First, you encode the data and you commit to it. Then you do something called a fast Fourier transform in order to find many more evaluations of the committed polynomials. Then you sort of distribute these evaluations and give different evaluations to different parties. And then afterwards, if you want to, you can reconstruct, where you can sort of say, if enough honest parties have seen some of the data, then we can reconstruct the full data. Actually defining what you want to do with data availability sampling is something which is a bit non-trivial, because even though it's very related to lots of concepts in the literature, it's not quite the same. So there has been some work into sort of figuring out what we want. And if you sort of go for different requirements and different things that you're like aiming to achieve, you will find that you end up with very different schemes. So what the goal is going to fundamentally impact what your final scheme ends up looking like. So back to sort of a couple more questions. Because of data availability, which is completely unrelated, we are now in a position where polynomial commitment schemes are going to be used on layer 1. Do you think that this will ease the transition to zero-knowledge proofs, considering they're like a fundamental building block, or do you think there's still lots of barriers? Maybe show of hands, who thinks yes? And who thinks no? I would probably be more interested by the no answer, I think. The other question, what is the best place for cryptographers to learn about the design goals behind candidate improvement proposals? Because in this situation, I'm sort of saying, well, with the case of data availability, if you do things differently, then you're going to end up with different schemes. Actually knowing what the core design goals are is like really very important. So do you think there's like a good place where these are well documented? Go on.
I'm not sure if that's the case, but isn't there the Ethereum Magician forum, sort of?
I don't know about that one, actually. What's the Ethereum Magician forum?
Maybe I get the name wrong, but with every EIPs, or most of them, there is a link to this forum where the author explains first in a post what the goal of the EIP is, and then there is some discussion.
Okay, that sounds like the perfect place. Thank you. Okay, I'm going to move on to sort of the final part of the talk, and this is going to be talking specifically about zero-knowledge specification. First, I'm going to mention a movement called ZKProof. And what this is a global movement to try and sort of standardize and mainstream advanced cryptography by building a community-driven trust ecosystem. So what we want to do is we want to, at this point, just build practical specifications, so not yet standards, just specifications of at least one zero-knowledge proving scheme. It would be good to have more, but at the moment, just one would be already a big improvement. And we're kind of considering that there are like multiple different layers to what you would need in this documentation, just because what we're trying to document is, well, has lots of layers. The starting layer is probably the one where things are moving at a very fast pace and is evolving quite quickly, and that's just getting the constraint system. So this is sort of saying, what am I trying to prove? If I want to prove that something's an encryption, how am I going to tell that to the circuit? If I want to prove that I've done this fully homomorphic operation correctly, how am I going to encode that in such a way that my proving scheme knows that this is what I'm trying to prove? So our first step is really sort of trying to describe the constraint system, specify it. There's sort of been mentioned that it would be a good idea maybe to do this in HackSpec, and do some basic checks to check that valid assignments pass, invalids fail, things like that. I would say that okay, you've described your constraint system, how are you then going to generate it, is something that we're not tackling right now, mostly because we don't know how to tackle it. I can't give a better answer than that. The next sort of 2 steps are to describe the actual snark logic. And this first goes through an optimizer. Many cryptographers are not aware of this step. I certainly was not aware of it for a long time. But it sort of says, if you have these constraints, you're not going to optimize by hand. That would be a stupid idea. We're going to do the optimizing as part of a backend for you. Only after that do you move on to sort of saying, what's the actual proving system? What does it look like? What operations do I need to do? How am I going to interact with these things? The proving system, by the way, is the only step that was really required for the shuffling argument, which I was describing earlier. So when I say that the shuffle argument is simpler, I really genuinely mean it. After that, you sort of take the proving system and you compile it. And this is the point where the polynomial commitment scheme comes in. And which polynomial commitment scheme you use entirely affects what your ending scheme is going to look like in some very fundamental ways. So for example, if you use the Frye polynomial commitment scheme, you get Starks. If you are going to use the KCG polynomial commitment scheme, you're going to have something pairing-based with a trusted setup. If you use something discrete log-based, then you're going to have something that doesn't require pairing, still requires group operations, but maybe has quite a large verifier. So really, this is the step where you can choose what you want for your scheme. So obviously, we've got quite a lot of choices here. Does anyone have any opinions on which polynomial scheme they think it would be important to write specifications for first? Do you think it would be better to have, for example, something with a big proof, but no trusted setup? Or do you think it would be better to have small proof and a trusted setup?
Hi, my name is Kenneth, and I'm really new in this blockchain industry, and I've been looking on zero-knowledge protocols because it's applicable outside of blockchain as well. So I think that the trusted setup would be a good start because it is something that is easily digest. It is easily to be digest for my brain, yeah.
Okay, so you find it the simplest one?
Yeah. Yes, that's correct.
That's fair. Arguably, pairings are not the most simple thing in the world, but thankfully we already have those. So, any other opinions? Cool. And does anyone have sort of any feelings on what they think the specifications should look like? Would you prefer something that's very easily digestible to somebody that's not necessarily that familiar with the space? Or would you prefer something that's very in the detail about every single layer, every single component that's being used? Go on.
I think the latter is better because that way we can really understand what's going on in the background.
Okay.
Sometimes when I don't have all the detail, it's very hard for me to, why we use this, why is that there?
So you even think that it would be easier to understand if there were all of the technical details than it would be if it was abstracted away?
Yes, yes.
Yeah. The final layer is applying hash functions. This, I would say, is a very major area for implementation bugs. For example, it's very important to avoid the situation where you have overlapping inputs, which is something that comes up quite frequently. So this, again, is an area where we want to be very careful and very precise about what we tell developers to implement. One current work on this is the Safe API. This is designed specifically for sponge hashes, so that would include SHA-3 and that would include Poseidon, but that would not include SHA-2. And yeah, the aim here is to sort of say, this is precisely what you can do. If you don't deviate from this at all, then you're probably not going to have too many implementation errors. I don't know if there's any other works within this area where people have been like trying to help people use hash functions in a good way. But if there is, do let me know about it. Maybe a hand up. If not, then I've come to the end of my slides. So I think this would be a time to ask me any more questions if you have any. Okay, I guess I've been asking lots as we've been going along. So thank you very much.
Thank you.